reviewing Thermo 1. So let's do 4-141. Okay. A piston cylinder device initially contains 0.35 kilograms of steam at 3.5 megapascals, superheated by 7.4 degrees Celsius. Now the steam loses heat to the surroundings, and the piston moves down, hitting a set of stops, at which point the cylinder contains saturated liquid water. The cooling continues until the cylinder contains water at 200 degrees Celsius. Determine A, the final pressure, and the quality if it's a mixture. B, the boundary work. C, the amount of heat transfer when the piston first hits the stops. And D, the total heat transfer. Okay, so we're going to solve a bunch here. All right, let's make our way through this. We have water. It says steam, but we'll go with water. We have a mass of 0.35 kilograms. We have a pressure initially at 3.5 megapascals. They give us this weird saying, if it's superheated, the steam's at 3.5 megapascals, superheated by 7.4 degrees Celsius. Okay, so that's a new thing. Okay, so I'll call that a delta T. It's superheated by 7.4 degrees Celsius. Okay. All right, and then it becomes, so the steam loses heat to the surroundings and the piston moves down, hitting a set of stops, at which point the cylinder contains saturated liquid water. Okay, so it hits the stops and it's a saturated liquid. So we have a quality of 0. Okay, so that's our second state. Okay. Then it keeps cooling and it gets to a temperature of 200 degrees Celsius. So that's a third state. Okay. They want us to find P3 and quality at 3, if it's a mixture. B is the boundary work. C is the heat transfer from 1 to 2, I'll call that. Okay, and then D is the total heat transfer. So that's the heat transfer from 1 to 3. Okay, let's draw our schematic. A set of stops here. We have a piston. Okay, there's some heat transfer. Set up our boundary. This is water in here. All right. Any assumptions we can put here? All right, so let's start with our analysis. All right, so part A is P3, so the pressure at state 3 and the quality at state 3, okay? All right, so where do we think we start to get to that pressure quality? Where do you want to begin?
Professor, can you repeat the question, please?
Yeah, part A is the pressure and the quality at state 3, right? So if we want to solve for that, where do we begin? What is the first thing we should do to get there?
Find P2.
So find our states, right? So you're looking at state, yeah, okay. All right, so let's go through our states. So we have state 1, which they gave us pressure 1. Right, so pressure 1, 3,500 kPa. And they gave us this weird delta superheated thing, okay? And that really just is that it's the temperature at 1 is equal to the Tsat at P1 plus this delta superheated, because it's saying it's superheated by this, our 7.4 degrees that we got. So that means it's above this saturation that we get at the pressure. Okay, so if we solve that, we have the Tsat, we look it up in our tables. This is 242.56, and then we add our 7.4. We get, let me do this below it. We got 250 degrees Celsius. Okay, so that means now we have pressure and we have temperature. Okay. And we find out, we know it's superheated, right? So superheated vapor. Okay, and if we wanted anything, we could go to the tables. A4, 5, 6, and 7, okay, because we have water, under the water tables. All right. So now state 2, we have a quality, right, 0, which is, tells us it's a saturated liquid. Okay. And then we need to figure out another independent intensive property to fix our state, right? So I'll go back up here. The problem itself wasn't very good at telling us about that, like the paragraph, but they did have the diagram, the schematic, and I have it there too. The same schematic they have. What do you guys think remains constant from state 1 to state 2? Any ideas?
The mass?
The mass does, yes, because it's closed system, right? But that's an extensive property, not an intensive property. So the mass does remain constant. There's no mass leaving, but we need to figure out an intensive property.
So the specific volume?
Not from 1 to 2, because the piston's moving down, right? So we're cooling, and the piston moves and hits the stops, state 2, right? So that means the volume will change, and if the mass is constant, then the specific volume, or sorry, the volume, then the specific volume changes. Okay.
Will the pressure stay the same then?
Yeah, the pressure will stay the same. Okay, and that's not. You know, I would prefer in the problem statement they said it was a constant pressure process or a weighted piston, right? That would tell us constant pressure process would obviously tell us pressure is constant. But a weighted piston also tells us that because the weight of the piston is not changing, so the force on the fluid is not changing. So from sum of forces, that means the pressure of the fluid wouldn't be changing. But the other thing that's showing it also is because they just have this piston there. They don't have, let me see if I can draw this better. a piece like that. And that's where it shows kind of like an external force you're putting on it, where you can vary the force, right? With like some kind of shaft, you can vary the force in the fluid. So that doesn't have it on that schematic that you gave, that was given, and that's saying there's only the weight of that piston, okay? So the pressure is being maintained constant, okay?
Professor,
Yes.
with the information we have so far, can't we just use this to figure out what the boundary work is right off the bat? Because this is, I'm assuming, just going to be a constant pressure process.
Yeah, and we could do that. We're gonna sort of part B. Yes, we'll
Yeah.
get to that.
Okay.
We'll do part A, and then yeah, we'll get to part B. Yep. All right, so we have pressure's the same, so that's 3,500 kPa at state 2, saturated liquid. So we can get anything we want at state 2, other properties now. We have two independent intensive properties. If we go to state 3 now, which is what we want, part A was asking for all that information, is now we see what we were given for state 3, 200 degrees Celsius, right? All right, so now we need another independent intensive property for state 3. And this is from 2 to 3. This is when the piston has hit the stops, okay? So what do we think is being maintained constant from 2 to 3?
Volume.
Volume, okay? So now volume in this case is constant. So mass is constant, so that means specific volume is also constant. So the specific volume at state 3 is the same as at state 2, right? So we would need to get the specific volume at state 2 then. And again, we have two independent intensive properties, so we can just go look this up in our tables. .001235 sounds made up. That's what the value is. All right, so now we have temperature, and now we have that same specific volume for state 3. Okay, so that means we have our state fixed at 3, and we can solve for our pressure and temperature is what they're asking for in part A, right? So if we use that
Pressure and quality,
oh,
I
sorry.
believe.
Yeah, pressure and quality, thank you. So if we use that specific volume, we're gonna see, and we check our tables, we're gonna have RV be greater than the VF, but less than the VG. Right? So that's for state 3 at 200 degrees Celsius. So that tells us it's what?
A sat mixture.
Saturated. Yep.
Yeah, yep. So we have a saturated mixture, okay? All right, so then that just means we got to solve our equation when we have a saturated mixture. All right, we get the VG at 200 degrees Celsius, the VF at 200 degrees Celsius. We have the specific volume, because it's 0.001235, and we can use that to solve for equality, okay? So we get a pretty small quality here, okay? And we know it's saturated, right? If it's saturated, that means it's at the saturation conditions. So P3 is Psat at 200 degrees Celsius. So that's, when we look that up, it's 1555 kPa. All right. So if you're kind of been a while since you take Thermo 1, or just need a refresher, this week is the week to refresh on Thermo 1. Maybe get, practice your properties. because we'll be using all those things continuously. Okay, so all right, so now we've solved for the quality and pressure 3, which was what was asked for up here. So we got part A down. Okay, part B was the boundary work, which was mentioned. So this is A. Part B was the boundary work, which was mentioned. We could have stopped and solved for that, right? So we have boundary work. So the boundary work will be the work boundary from 1 to 2, plus the boundary work from 2 to 3. Okay, does either of those cancel out?
Boundary work from 2 to 3 cancels out.
Yeah, so 2 to 3 cancels. It goes to 0 because there's no change in volume, right? Boundary work requires your volume to change for there to be boundary work. Okay, so no boundary work, or no volume change, no boundary work. Okay, so then we just have 1 to 2. Okay, and what do we get to do here? What type of process do we have?
Constant pressure process.
Yeah, so we have a constant pressure process, our second favorite type of boundary work process, right? First favorite is obviously the constant volume one, because we get to just make it 0 and simplify. Next is our constant pressure, because P goes outside of the integral, and we just have our P delta V, right? Which we can pull the mass out and make it specific volume change. Okay, since mass is the same, we have change in specific volume. If we look, the problem was given mass. We have pressure at 1, right? We have specific volume 2 because we needed it for 3. We don't have the specific volume at 1 yet, but we fixed our state. So now it's just a matter of going and get it. Okay, so we can go and get the specific volume at 1. Okay, which I might not be able to fit this right there. 0.05875 meters cubed per kilogram. Okay, which doesn't look as fake as the other specific volume, right? All right. So now we have specific volume at state 1. So we can plug in and solve, and we get negative 70.45 kilojoules. Does that work in or work out?
Work out.
It happens to be work in, okay, because first, there's a couple things to show us it's negative, okay. V2, specific volume in state 2, is smaller than 1, so it's compressing, okay. So if we're compressing, it's work in also. So we're compressing, so volume 2 is less than volume 1, so we're compressing, we're putting work into the system. Okay. So that's a work in. The negative tells us it's work in too. Okay. All right, so we have solved the boundary work. So part C is the heat transfer from 1 to 2. Okay. How do we solve that? Where do we start?
Conservation of energy.
Yeah, so our COE, and it's a closed system, right? We have our fixed mass that was mentioned. So we have a closed system. Okay. And this is from 1 to 2, 1 to 2, 1 to 2. All right, so we have no kinetic, no potential, because it's not accelerating off into space, or it's not like a car going up and down a hill, which would have kinetic energy and potential energy changes of the system. So we have our neglect kinetic energy and potential energy assumption. Okay. Yeah, let's get back down there. All right, from 1 to 2. Just moving some stuff around. To solve for Q 1 to 2. Mass was given, so we have mass, right? We just solved for work from 1 to 2, so we have that. We need to get U1 and U2, right? Specific volumes of state 1, state 2. So we go back up, put in U1, go to our tables. So we have 26, 23.9. And we have 1045.4. So now we have those. Okay, so we can plug values in, plug them straight in, and solve, and we get a negative 622.9 kilojoules. Is that heat in or heat out?
Heat out.
Yeah, it's heat out. Okay. All right, so the thing to see is basically right here, and I have basically a positive there in front of the Q12. So I was assuming it was heat in, right? By having a positive value in front of Q12. Then I solved with algebra and substitute everything in, and I got a negative. So I got the opposite of what I assumed at the beginning, which is heat out. Okay, so that's negative means it's heat out because I assumed heat in at the beginning, right? Same thing occurs with work. You have a negative there, so you're assuming its work out is a positive value because of that. So if you solve and you get a positive value out, you got work out. If you solve and you get a negative value, you get the opposite of what you assumed. Okay, so you get a work in. All right, so then we need Q1 to 2, or sorry, the total heat transfer, which is Q from 1 to 3. Okay. What do we do to get that?
Wouldn't it be the same as the previous section, the previous part?
What we do the same thing or the same value?
That's what I was. That's what I'm asking. Like, is it going to be the same value, or delta U would have a different value for state 3? Correct?
Yes, because now we could go. So there's two ways to actually solve for Q13. You could either do solve for 1 to 2, or let's do 1 to 3 is equal to Q 1 to 2 plus Q 2 to 3, right? And so then you would just solve for Q 2 to 3, right? Or you could solve actually for this directly, which is what I'm going to show. Yeah, so we would do the COE closed system like the previous one, right? But I'm going to do just directly from 1 to 3, okay? And already we have kinetic and potential neglected. All right, from 1 to 3 is equal to then our, we have our mass, delta U, we have,
Wouldn't that be just work from 1 to 2 because there is no work done?
correct.
after that?
Yeah, so we already solved for work 1 to 3 is the same as work 1 to 2, right? Yep. So that is the same as work 1 to 2, okay? But I'll just substitute that value in, okay? So, but we can make that note too. Okay. All right, so then that means we have this. We have U2, we just need U3, okay? So we go up here, go to our state, it's fixed. We go to our tables and get our value. We get 851.55. So now we have, everything. So now we can plug our values straight in, and we get negative 690.8 kilojoules, which again, we have our negative number. So it's heat out. Okay. The other thing you could have done is the COE of the closed system from 2 to 3, right? Then there would be no work, and then you just have the delta U from 2 to 3, and you'd have then the Q from 2 to 3, and you'd need to add that to the 1 to 2, and you get the same. Okay, since energy is conserved, as long as you're using the right terms during the right process, it all adds up, right? So that way it would also be, you'd get the same answer. Okay. Any questions?
Oh yeah, Professor. Real quick, why is it that you used U2 when calculating Q1 to 3?
Oh, sorry, that is right. Yeah, thank you.
Okay, cool.
Thinking about the other one. Yeah, this should be.
I do have one more question. So for part B, when we were calculating the boundary work, right, could we have also used the isothermal compression equation?
No, because that one is an isothermal boundary work of an ideal gas.
Okay, okay.
So it uses the ideal gas equation, and we're a constant pressure process. So you'll see that doesn't follow the same thing there. Okay.
Okay, thank you.
Mm-hmm. All right, so then last thing, and you'll kind of see this a little bit more too when we get to the, is I want to do some diagrams. I'll do you see a little bit of it in this explanation. So let's do PV. In the TV. Okay. So starting with the PV diagram, we go back up and we check out our states, right? So we have superheated, right? And we have a saturated liquid, state 2, and then we have a saturated mixture, okay? All right, so state 1 is superheated, state 2 is sat mix. I'm going to start with state 2 because it's a nice, easy point. Okay, so I know that one is a saturated mixture, so it's on the left of the dome. So that's state 2. 1 goes to 2, it's a superheated, and what was being maintained constant again from 1 to 2?
Pressure.
Pressure. So that means we know we're a horizontal line, right? Horizontal line and superheated. So that means we should be over here. We should be going from right to left because that's the only way to be superheated in a constant pressure. Okay. Now we had our constant volume process. So that means we have a vertical line. So we can either go up or down then. If it's constant volume, we can either go up or down, right? And we're a saturated mixture, so that means we have to go down, okay? We're not compressed, so we're going down, right? So let's see how awful my vertical line will be. Too bad. All right, so then we have our state 3, okay? That means we have T1 here, line, this is our T2 line, and this is our T3 line, which is 200. Celsius. T1 was 250, and T2 is just greater than T3. Okay, so that's our PV diagram. Okay. So now we have our TV diagram. Okay. And again, we can start with our saturated mixture value. And we have a constant pressure process. Well, these are constant pressure lines, so this one's a whole easier. We have our superheated at state 1. So we follow along, okay? And then it's constant volume. So we go down. Because temperature and pressure is linked, it looks very similar inside the dome. Okay, so now we have P1 equals P2. And we have P3. Okay. And you can see the process that's happening, right? 1 to 2, if we look at the PV diagram, that's our boundary work, right? And that's the area under 1 to 2 is our boundary work. And then 2 to 3 is a vertical line, there's no boundary work, so there's no area under that curve, right? And 1 to 2, you don't see the volume, temperature is not being maintained constant, it's just pressure, right? And then it's changing phase. We don't have an ideal gas inside there. Okay. Any questions? All right, so let's do 5-78E. Steam is to be condensed on the shell side of a heat exchanger at 75 degrees Fahrenheit. Cooling water enters the tube at 50 degrees Fahrenheit at a rate of 45 pounds per second and leaves at 65 degrees Fahrenheit. Assuming the heat exchanger to be well insulated, determine the rate of heat transfer in the heat exchanger and the rate of condensation of the steam. Okay. All right, so we have on one side of this heat exchanger, we have steam, which is condensing, so the temperature is going to be the same, which is 75 degrees Fahrenheit. Okay. If it's condensing, it's going from a saturated vapor at state 3 to a saturated liquid. Okay. we have the water side, which I'll call state 1 is 50 degrees Fahrenheit, and then we have state 2 being 65 degrees Fahrenheit, so the outlet of the water. And then the mass flow rate of the water is 45 pounds mass per second. And then it's also well insulated. Okay, they want us to find the rate of heat transfer. So that's inside the heat exchanger. And then the condensation rate of the steam. That is just the mass rate of the steam, the amount that's condensing. Okay. All right, schematic. So we have the inlet of the steam. Oh, I call that 3. The outlet of the steam, call that 4. We have the inlet of the water, state 1, and the outlet of the water, state 2. Okay. So assumptions, it's adiabatic, right? It's well insulated, so we're going to assume the heat exchanger is adiabatic. So I'm going to put my kind of insulation line here. Okay, so now we want to find, we'll start with the rate of heat transfer inside the heat exchanger, right? So how do we start, or what do we do to solve for that? All right, so we're not looking for the rate of heat transfer outside of the heat exchanger, right? Because that's well insulated. So to the outside, it's well insulated. So now we got to think about the heat transfer inside, okay? So that, go ahead.
You can do the conservation of energy between the 2 like pipes.
Well, yes, so we got to do, so that means we got to select our boundary as either the steam or the water, okay? So somewhere between, right? So we either got to select the steam as our boundary or the water as our boundary. Okay, so which one do we think would be our better choice here?
Water we have. Can we use the tables for the water?
Potentially, yeah. There's a couple ways we can get the water values, yeah.
The steam has a constant temperature, so I honestly, does it really matter? What it doesn't, right?
It does.
Oh.
If so, if we started with one of them, we'll hit a roadblock and have two unknowns. Okay, and then we'll have to go to the other one. And it's based upon what we do here is just, it's more of what has more givens, right? So we could go down the steam path of using conservation energy around the steam, but we don't have a mass flow rate. That's actually what we're solving for the next part. So we're going to have an unknown of the mass flow rate and the heat transfer. Okay, so then we would have to know that and stop right there, and then go to the COE on the heat on the water then. Okay, so let's draw our boundary then. So there's our boundary, right? And this has heat transfer, right? Because that's inside. So there's heat transfer crossing our boundary of the water. So we do our COE open system because we have mass flow rate crossing our boundary. Okay, because there's water going in and crossing our boundary, and water coming out and crossing our boundary. Okay. All right, so we have our open system conservation energy, everything crossing our boundary and energy on the left, what's going on inside our boundary on the right. So what can we cancel or neglect?
Oh, we can neglect work or power, W dot.
Yeah, there's no work inside our boundary. We don't see any resistance heater, paddle wheels. It's not growing or shrinking in volume, so we don't have any work, right?
I'm assuming that there's no height change, so we can also neglect potential energy.
Yeah, neglect kinetic or potential energy because we're assuming that the height change is negligible compared to the other energies. Okay.
In that case, we could also neglect kinetic energy too, correct?
Yeah, so we don't have any information on velocities in and out, but they're probably in a heat exchanger. They're not going to change much, the difference between the inlet and outlet velocity. Okay, so the change in kinetic energy from inlet to outlet's not going to be high. All right, so then you know that. Anything else?
Is this system a steady state?
Yeah, so we would assume steady state. We're not starting it up or shutting it down, so we're not filling it with mass, or which would be then filling it with energy, or emptying it. We've reached it, and it's just the inlet and outlets are just at the same rate. So that means the system inside is steady state. The amount of energy is not changing with respect to time. Okay. All right, so that means we have steady state. We have neglect kinetic energy and potential. Okay, we don't have to put the work there because it's just not on our schematic. It's not an assumption. It's just not there. Okay. All right, so now we're left with this, right? So what would be our next thing to do then?
Place that M1 or mass flow rate around mass flow rate 1, mass flow rate 2 are the same.
Yes, so from our conservation of mass, it's again steady state. So there's no mass change. The amount of mass inside the system is not changing with respect to time. We're not filling, we're not emptying. We only have one inlet and one outlet on that boundary. Okay, so mass flow rate 1 is equal to 2. We can also look at it and do mass flow rate 3 is equal to 4. Okay. All right, so if we apply that, move that around. All right. We are looking for the heat transfer, right? So we have that on the left. We have the mass flow to water. We got to figure out our enthalpies. Okay, and there's actually 2 ways of doing it this time for this part. So earlier, someone mentioned the tables, right? So that's one of them, okay? Delta H, we have tables, which we need 2 independent intensive properties. So we have T1 and T2. We would need another independent intensive property to get from the tables. So we would have to assume a P1 and a P2, where we would say P1 is equal to, let's say, 14.7 PSI, so atmospheric pressure. And then we could use that pressure. We have a temperature, we could look up the enthalpy in the tables. Okay. There's another method here. We are at 50 degrees Fahrenheit and 65 degrees Fahrenheit. And if we're assuming it's at atmospheric pressure, this water, we're not anywhere near the boiling point of water, right? We're in that compressed region. We're well in that compressed region, not even approaching the boiling point. So we can assume this water is what in that case?
Saturated liquid?
Not saturated liquid. So
Compressed liquid.
yeah, a compressed liquid or basically we can then say it's incompressible substance. If it just stays in that region on the left, we can say it's an incompressible substance. Okay, and then we have that section on our equation sheet, which simplifies. Okay, and that's where delta U, C delta T, and delta H is C delta T plus V delta P, and we're assuming there's no pressure drop in the tubes. Okay. So let's put that up there. All right, so now we have this part. That's T2. Okay. All right, so we have T1, T2, the mass rate of this is water. Okay, so then we just need the specific heat. Okay, we can get that in the back. Okay, so we get 1 BTUs per pound mass degrees Fahrenheit. That means we got everything. We get plug in, we get a rate of heat transfer of negative 675. Oh, sorry, not negative, positive 675 BTUs per second, which is heated. All right, so we have the rate of heat transfer occurring inside the system. All right, I'm gonna kind of go quick because I only got a minute here, or two. So part B is the mass condensation rate of the steam. Okay, and that's just doing then the COE open system steam side. So now our boundary is the steam. We're going to end up with mass flow rate of rate of heat transfer, and we're going to get steam H3 minus H4. So similar kind of simplification that we saw for the water side. Okay, so then we're solving for the steam. We have the heat transfer because it just ends up being negative 675 because the heat is leaving the steam side. Okay, then we just need our H's. Okay, so this, we go back up. Excuse me, we saw 75 degrees Fahrenheit and we have equalities. So we can get our enthalpies in the back for H3 and H4. We'll also see that'll be equal to that. Let's do this. H4 minus H3 is equal to HFG at T equals 75 degrees Fahrenheit. So you could either use HFG or get your H3 and H4 from the states and solve and we get 0.675 BTUs per second. Okay, any questions on that? I know I rushed through that part just because we're running out of time. I should say. Okay. Any questions?
So you can't assume the stream or the steam is a ideal gas, like
No, no. So because it isn't. It's they say steam, and it's very vague. Steam could mean it is superheated, it has a quality, it's pressure. So in this case, it's going from a saturated liquid to a saturated vapor. If you assumed, or from a saturated vapor to saturated liquid, if you assumed it was an ideal gas, you would have Cp delta T, and the temperature isn't changing, so there'd be 0 Q. In reality, there's a ton of heat transfer when you're changing phase. So that's 675. That's a ton of heat transfer when you're changing phase. So it's going from a saturated vapor to saturated liquid. So if you assume it's an ideal gas, you're going to be extremely incorrect on this one. So whenever it's water or steam, you always want to first start with tables are always right. Ideal gas in compressed substance is sometimes right. Okay. So you got to know when you can simplify to something like that. And steam is a very vague term that people use, and it could be in the superheated region, it could be in the inside the dome. Okay, and when you're inside the dome, there's tons of latent energy. Okay. Other questions? That was a good question. All right, well then that's it. And we'll see on Wednesday, we'll continue doing some review examples. Okay, so, and I should be posting the homework, suggested homework, and then the ones that you need to submit tomorrow, I hope, okay, for this first exam, what the problems would be. All right, well, that's it. If you have any additional questions, let me know. We can set up a Zoom talk and have anything that's needed there. Okay. All right. Have a good one.
See you, Professor.
Thanks.
Yep.
Thanks, you too. Have a nice day.
No problem. Yep.